People have always wanted answers to the big questions. Where did we come from? How did the universe begin? What is the meaning and design behind it all? Is there anyone out there? I am a scientist with a deep fascination with physics, cosmology, the universe, and the future of humanity. I have spent my life traveling across the universe inside my mind. Through theoretical physics, I have sought to answer some of the great questions. It has been a glorious time to be alive and doing research. Our picture of the universe has changed a great deal in the last 50 years, and I'm happy if I have made a contribution. One of the great revelations of the space age has been the perspective it has given humanity on ourselves. When we see the Earth from space, we see ourselves as a whole. It is such a simple image with a compelling message. One planet, one human race. I was born exactly 300 years after the death of Galileo, and I grew up in a tall, narrow Victorian house in Highgate, London, until my family relocated to the cathedral city of St Albans. I went to St Albans School. I was never more than about halfway up the class. It was a very bright class. But my classmates gave me the name Einstein, so presumably they saw signs of something better. I had 6 or 7 close friends in St Albans, and I remember having long discussions and arguments about everything from radio-controlled models to religion. One of the big questions we discussed was the origin of the universe, and whether it required a god to create it and set it going. My father encouraged my interest in science, and as he himself had gone to University College, Oxford, he thought I should apply there too. At that time, University College had no fellow in mathematics, so I had little option but to try for a scholarship in natural science. I surprised myself by being successful. I was 20 in October 1962, when I arrived in Cambridge for graduate studies at the Department of Applied Mathematics and Theoretical Physics. I had applied to work with Fred Hoyle, the most famous British astronomer of the time. However, Hoyle had enough students already, so to my great disappointment I was assigned to Dennis Sharma, of whom I had not heard. But it was just as well I hadn't been a student of Hoyle, because I would have been drawn into defending his steady-state theory, a task which would have been harder than negotiating Brexit. As some of you may have seen from the film in which Eddie Redmayne plays a particularly handsome version of me, in my 3rd year at Oxford, I noticed that I seemed to be getting clumsier. I was home for the Christmas break when my mother persuaded me to go skating on the lake in St Albans. I fell over and had great difficulty getting up again. I spent weeks in St Bartholomew's Hospital in London and had many tests. At some point I must have learned that the diagnosis was amyotrophic lateral sclerosis, ALS, a type of motor neuron disease in which the nerve cells of the brain and spinal cord atrophy and then scar or harden. I also learned that people with this disease gradually lose the ability to control their movements, to speak, to eat, and eventually to breathe. Understandably, I became depressed and couldn't see the point of continuing to research my PhD, because I didn't know if I would live long enough to finish it. But then the progression of my illness slowed down, and I had a renewed enthusiasm for my work. While there's life, there's hope. And of course, there was also a young woman called Jane, whom I had met at a party. She was very determined that together we could fight my condition. Getting engaged lifted my spirits, and I realized if we were going to get married, I had to get a job and finish my PhD. To support myself during my studies, I applied for a research fellowship at Gonville and Caius College. I was elected, and the fellowship meant that I could continue my research despite my increasing disability. It also meant that Jane and I could get married, which we did in July 1965. The big question in cosmology in the early 1960s was, did the universe have a beginning? Many scientists were instinctively opposed to the idea because they felt that a point of creation would be a place where science broke down. One would have to appeal to religion and the hand of God to determine how the universe would start off. This was clearly a fundamental question, and it was just what I needed to complete my PhD thesis. Roger Penrose had shown that once a dying star had contracted to a certain radius, there would inevitably be a singularity, that is, a point where space and time came to an end. Surely, I thought, we already knew that nothing could prevent a massive cold star from collapsing under its own gravity until it reached a singularity of infinite density. A eureka moment came in 1970, a few days after the birth of my daughter, Lucy. While getting into bed one evening, I realized that I could apply to black holes the causal structure theory I had developed for singularity theorems. If general relativity is correct, and the energy density is positive, the surface area of the event horizon, the boundary of a black hole, has the property that it always increases when additional matter or radiation falls into it. Moreover, if two black holes collide and merge to form a single black hole, the area of the event horizon around the resulting black hole is greater than the sum of the areas of the event horizons around the original black holes. In 1973 came the publication with George Ellis of our book, The Large-Scale Structure of Space-Time. My work with Penrose had shown that general relativity broke down at singularities, so the obvious next step would be to combine general relativity, the theory of the very large, with quantum theory, the theory of the very small. In particular, I wondered, can one have atoms in which the nucleus is a tiny primordial black hole formed in the early universe? My investigations revealed a deep and previously unsuspected relationship between gravity and thermodynamics, the science of heat, and resolved a paradox that had been argued over for 30 years without much progress. How could the radiation left over from a shrinking black hole carry all of the information about what made the black hole? To answer this, I studied how quantum fields, or particles, would scatter off a black hole. I was expecting that part of an incident wave would be absorbed and the remainder scattered. But to my great surprise, I found there seemed to be emission from the black hole itself. The emission of this thermal radiation from the black hole is now called Hawking radiation, and I'm proud to have discovered it. In 1974, I was elected a Fellow of the Royal Society, and in 1979 I was elected to the Lucasian Professorship of Mathematics, a post once held by Sir Isaac Newton and Paul Dirac. By the early 1980s, I endured prolonged choking fits because my larynx was weakening, and in 1985 I caught pneumonia on a trip to CERN, the European Organization for Nuclear Research in Switzerland. I was rushed to the Lucerne Cantonal Hospital and put onto a ventilator. The doctors suggested to Jane that they turn off my ventilator to end my life, but Jane refused and had me flown back to Addenbrooke's Hospital in Cambridge by air ambulance. Thankfully, the doctors at Addenbrooke's tried hard to get me back to how I had been before the visit to Switzerland, However, they had to perform a tracheostomy, which took away the ability to speak. Luckily, a computer expert in California named Walt Waltos heard of my difficulties. He sent me a computer program he had written called Equalizer. This allowed me to select whole words from a series of menus on the computer screen on my wheelchair by pressing a switch in my hand. Today I use a program called ACAT, developed by Intel, which I control by a small sensor in my glasses via my cheek movements. It has a mobile phone, which gives me access to the internet. I can claim to be the most connected person in the world. I have kept the original speech synthesizer I had, however, partly because by now I identify with this voice, despite its American accent. Appropriately enough, A Brief History of Time was first published on April Fool's Day in 1988. Not everyone may have finished it or understood everything they read, but they at least grappled with one of the big questions of our existence and got the idea that we live in a universe governed by rational laws that, through science, we can discover and understand. To my colleagues, I'm just another physicist, but to the wider public, I became possibly the best-known scientist in the world. I had my biggest ever audience when I opened the Paralympic Games in London in 2012. I have led an extraordinary life on this planet, while at the same time travelling across the universe by using my mind and the laws of physics. I have been to the furthest reaches of our galaxy, travelled into a black hole, and gone back to the beginning of time. On Earth, I have experienced highs and lows, turbulence and peace, success and suffering. I have been rich and poor, I have been able-bodied and disabled. But it would be an empty universe indeed if it were not for the people I love and who love me. But there are other big questions on the planet which must be answered. How will we feed an ever-growing population? Provide clean water, generate renewable energy, prevent and cure disease, and slow down global climate change. We are all time travellers, journeying together into the future. But let us work together to make that future a place we want to visit. Be brave, be curious, be determined. Overcome the odds. It can be done. Science is increasingly answering questions that used to be the province of religion. Religion was an early attempt to answer the questions we all ask. Why are we here? Where did we come from? Long ago, the answer was almost always the same. Gods made everything. The world was a scary place, so even people as tough as the Vikings believed in supernatural beings to make sense of natural phenomena, like lightning, storms, or eclipses. Nowadays, science provides better and more consistent answers, but people will always cling to religion because it gives comfort, and they do not trust or understand science. A few years ago, the Times newspaper ran a headline on the front page which said, "Hawking, God did not create universe." God was shown in a drawing by Michelangelo looking thunderous. They printed a photo of me looking smug. They made it look like a duel between us. But I do not want to give the impression that my work is about proving or disproving the existence of God. If you believe in science, you believe that there are certain laws that are always obeyed. In about 300 BC, a philosopher called Aristarchus was fascinated by eclipses of the moon. Aristarchus studied the heavens carefully and realized the eclipse was really the shadow of the earth passing over the moon, and not a divine event. Aristarchus suggested that stars were not chinks in the floor of heaven, as his contemporaries believed, but that stars were other suns, like ours, only a very long way away. What a stunning realization it must have been. The universe is a machine governed by principles or laws that can be understood by the human mind. Unlike laws made by humans, the laws of nature cannot be broken. That's why they are so powerful, and, when seen from a religious standpoint, controversial too. If you accept, as I do, that the laws of nature are fixed, then it doesn't take long to ask, what role is there for God? The one remaining area that religion can now lay claim to is the origin of the universe. But even here, science is making progress and should soon provide a definitive answer to how the universe began. I published a book that asked if God created the universe, and that caused something of a stir. I think the universe was spontaneously created out of nothing, according to the laws of science. Despite the complexity and variety of the universe, it turns out that to make one, you need just 3 ingredients. The first ingredient is matter, stuff that has mass. Matter is all around us, in the ground beneath our feet and out in space. Dust, rock, ice, liquids, vast clouds of gas, massive spirals of stars. The second thing you need is energy. Look up at the sun and you can feel it on your face. Energy produced by a star 93 million miles away. Energy permeates the universe, driving the processes that keep it a dynamic, endlessly changing place. The third thing we need to build a universe is space. Wherever we look, we see space, more space and even more space. So where could all this matter, energy and space come from? The answer came from the insights of one man, probably the most remarkable scientist who has ever lived. His name was Albert Einstein. Sadly, I never got to meet him, since I was only 13 when he died. Einstein realized that 2 of the main ingredients needed to make a universe, mass and energy, are basically the same thing. His famous equation E equals mc squared simply means that mass can be thought of as a kind of energy and vice versa. So instead of 3 ingredients, we can now say that the universe has just 2, energy and space. So where did all this energy and space come from? The answer was found after decades of work by scientists. Space and energy were spontaneously invented in an event we now call the Big Bang. At the moment of the Big Bang, an entire universe came into existence, and with it, space. So how does an entire universe full of energy, the awesome vastness of space and everything in it, simply appear out of nothing? For some, this is where God comes back into the picture. Big Bang was the moment of creation, but science tells a different story. The secret lies in one of the strangest facts about our cosmos. The laws of physics demand the existence of something called negative energy. Imagine a man wants to build a hill on a flat piece of land. The hill will represent the universe. To make this hill, he digs a hole in the ground and uses that soil to dig his hill. But of course, he's not just making a hill, he's also making a hole. In effect, a negative version of the hill. The stuff that was in the hole has now become the hill, so it all perfectly balances out. This is the principle behind what happened at the beginning of the universe. When the Big Bang produced a massive amount of positive energy, it simultaneously produced the same amount of negative energy. In this way, the positive and the negative add up to zero. Always. It's another law of nature. So where is all this negative energy today? It's in space. According to the laws of nature concerning gravity and motion, laws that are among the oldest in science, space itself is a vast store of negative energy, enough to ensure that everything adds up to zero. The endless web of billions upon billions of galaxies, each pulling on each other by the force of gravity, acts like a giant storage device. The universe is like an enormous battery storing negative energy. The positive side of things, the mass and energy we see today, is like the hill. The corresponding whole, or negative side of things, is spread throughout space. This means that if the universe adds up to nothing, then you don't need a God to create it. What could cause the spontaneous appearance of a universe? At first it seems a baffling problem, but travel down to the atomic level and right down to the subatomic level, and you enter a world where conjuring something out of nothing is possible. That's because, at this scale, particles such as protons behave according to the laws of nature we call quantum mechanics, and they really can appear at random, stick around for a while, and then vanish again, to reappear somewhere else. Since we know the universe itself was once very small, perhaps smaller than a proton, it means the universe itself, in all its mind-boggling vastness and complexity, could simply have popped into existence without violating the known laws of nature. From that moment on, vast amounts of energy were released as space itself expanded, a place to store all the negative energy needed to balance the books. But of course, the critical question is raised again. Did God create the quantum laws that allowed the Big Bang to occur? I think science has a more compelling explanation than a divine creator. Our everyday experience makes us think that everything that happens must be caused by something that occurred earlier in time. So it's natural for us to think that something, maybe God, must have caused the universe to come into existence. But when we're talking about the universe as a whole, that isn't necessarily so. The laws of nature itself tells us that not only could the universe have popped into existence without any assistance, and have required nothing in terms of energy, but also that it is possible that nothing caused the Big Bang. Nothing. The explanation lies back with the theories of Einstein and his insights into how space and time in the universe are fundamentally intertwined. Something very wonderful happened to time at the instant of the Big Bang. Time itself began. To understand this mind-boggling idea, consider a black hole floating in space. A typical black hole is a star so massive that it has collapsed in on itself. It's so massive that not even light can escape its gravity, which is why it's almost perfectly black. Its gravitational pull is so powerful, it warps and distorts not only light, but also time. Inside the black hole, time itself doesn't exist. And that's exactly what happened at the start of the universe. The role played by time at the beginning of the universe is, I believe, the final key to removing the need for a grand designer and revealing how the universe created itself. As we travel back in time towards the moment of the Big Bang, the universe gets smaller and smaller and smaller, until it finally comes to a point where the whole universe is a space so small that it is, in effect, a single infinitesimally small, infinitesimally dense black hole. And, just as with modern-day black holes floating around in space, the laws of nature dictate something quite extraordinary. They tell us that here too, time itself must come to a stop. You can't get to a time before the Big Bang because there was no time before the Big Bang. For me, this means that there is no possibility of a creator, because there is no time for a creator to have existed in. Do I have faith? It's my view that the simplest explanation is that there is no God. No one created the universe, and no one directs our fate. There is probably no heaven and afterlife either. I think that when we die, we return to dust. But there's a sense in which we live on in our influence and in our genes that we pass on to our children. We have this one life to appreciate the grand design of the universe, and for that, I am extremely grateful. Why should we go into space? The obvious answer is because it's there, all around us. Not to leave planet Earth would be like castaways on a desert island, not trying to escape. We need to explore the solar system to find out where humans could live. Spreading out into space will completely change the future of the human race and maybe determine whether we have any future at all. We could have a base on the moon within 30 years, reach Mars in 50 years, and explore the moons of the outer planets in 200 years. By reach, I mean in spacecraft, with humans aboard. We thought space was worth a big effort in the 1960s. In 1962, President Kennedy committed the US to landing a man on the moon by the end of the decade. On the 20th of July 1969, Buzz Aldrin and Neil Armstrong landed on the surface of the moon. I was 27 at the time, a researcher at Cambridge, and I missed it. I was at a meeting on singularities in Liverpool and listening to a lecture by René Thom on catastrophe theory when the landing took place. My son, aged 2, described it to me. Many of today's scientists were inspired to go into science as a result of the moon landings. However, after the last moon landing in 1972, with no future plans for further manned space flight, public interest in space declined. A new crewed spaceflight program would do a lot to restore public enthusiasm for space, a goal of a base on the moon by 2050 and of a manned landing on Mars by 2070 would reignite the space program. In late 2017, Elon Musk announced SpaceX plans for a lunar base and a Mars mission by 2022, and President Trump signed a space policy directive refocusing NASA on exploration and discovery. So, perhaps we'll get there even sooner. I have always dreamed of spaceflight, but for so many years I thought it was just that, a dream. Confined to Earth and in a wheelchair, how could I experience the majesty of space except through imagination and my work in theoretical physics? But I had not factored in the enthusiasm of individuals whose mission it is to take that first step in venturing outside Earth. And in 2007, I was fortunate enough to go on a zero-gravity flight and experience weightlessness for the first time. It only lasted 4 minutes, but it was amazing. Our experience with the ISS, the International Space Station, shows that it is possible for human beings to survive for many months away from planet Earth. However, the zero gravity of orbit causes a number of undesirable physiological changes, including a weakening of the bones. One would therefore want any long-term base for human beings to be on a planet, or moon. By digging into the surface, one would get thermal insulation and protection from meteors and cosmic rays. The planet or moon could also serve as a source of the raw materials that would be needed if the extraterrestrial community was to be self-sustaining, independent of Earth. What are the possible sites of a human colony in the solar system? The most obvious is the moon. It is close by and relatively easy to reach. On the other hand, the moon is small, and without atmosphere or a magnetic field to deflect the solar radiation particles, as on Earth. There is no liquid water, although there may be ice in the craters at the North and South Poles. A colony on the moon could use this as a source of oxygen, with power provided by nuclear energy or solar panels. The moon could be a base for travel to the rest of the solar system. Mars is the obvious next target. It once had a magnetic field, but it decayed 4 billion years ago, leaving Mars without protection from solar radiation. This stripped Mars of most of its atmosphere. However, the pressure must have been higher in the past, because we see what appear to be runoff channels and dried-up lakes. There is no sign of life on Mars now, but if we found evidence that life had once existed, it would indicate that the probability of life developing on a suitable planet was fairly high. NASA has sent a large number of spacecraft to Mars, starting with Mariner 4 in 1964. It has surveyed the planet with a number of orbiters. These orbiters have revealed deep gullies and the highest mountains in the solar system. NASA has also landed a number of probes on the surface of Mars, most recently the 2 Mars rovers. These have sent back pictures of a dry desert landscape. There has been volcanic activity on Mars. This would have brought minerals and metals to the surface, which a colony could use. The Moon and Mars are the most suitable sites for space colonies in the solar system. Mercury and Venus are too hot, while Jupiter and Saturn are gas giants with no solid surface. Titan, a moon of Saturn, is larger and more massive than our moon and has a dense atmosphere. The Cassini-Huygens mission of NASA and the European Space Agency has landed a probe on Titan, which has sent back pictures of the surface. However, it is very cold, being so far from the sun, and I wouldn't fancy living next to a lake of liquid methane. But what about our boldly going beyond the solar system? Our observations indicate that a significant fraction of stars have planets around them. So far we can detect only giant planets like Jupiter and Saturn, but it is reasonable to assume that they will be accompanied by smaller Earth-like planets. Some of these will lie in the Goldilocks zone, where the distance from the star is in the right range for liquid water to exist on their surface. There are around 1,000 stars within 30 light-years of Earth. If 1% of these have Earth-sized planets in the Goldilocks zone, we have 10 candidate new worlds. Take Proxima b, for example. This exoplanet, which is the closest to Earth but still 4.5 light-years away, orbits the star Proxima Centauri within the solar system Alpha Centauri, and recent research indicates that it has some similarities to Earth. Travelling to these candidate worlds isn't possible perhaps with today's technology, but by using our imagination, we can make interstellar travel a long-term aim in the next 200 to 500 years. According to NASA, and the speed at which we can send a rocket, it would take as little as 260 days to reach Mars, give or take 10 days, with some NASA scientists predicting as little as 130 days. But it would take 3 million years to get to the nearest star system. To go faster would require a much higher exhaust speed than chemical rockets can provide. That of light itself. In other words, with current technology, interstellar travel is utterly impractical. We have a chance to change that, thanks to imagination and ingenuity. In 2016, I joined with the entrepreneur Yuri Milner to launch Breakthrough Starshot, a long-term research and development program aimed at making interstellar travel a reality. If we succeed, we will send a probe to Alpha Centauri within the lifetime of people alive today. So far, our explorations have been limited to our local cosmic neighbourhood. 40 years on, our most intrepid explorer, Voyager, has just made it to interstellar space. Its speed, 11 miles a second, means it would take about 70,000 years to reach Alpha Centauri. Breakthrough Starshot is a real opportunity for man to make early forays into outer space, with a view to probing and weighing the possibilities of colonization. It is a proof-of-concept mission and works on 3 concepts: miniaturized spacecraft, light propulsion, and phase-locked lasers. The Starship, a fully functional space probe reduced to a few centimeters in size, will be attached to a light sail. Made from metamaterials, the light sail weighs no more than a few grams. It is envisaged that 1,000 starships and light sails, the nanocraft, will be sent into orbit. On the ground, an array of lasers at the kilometre scale will combine into a single, very powerful light beam. The beam is fired through the atmosphere, striking the sails in space with tens of gigawatts of power. The idea behind this innovation is that the nanocraft ride on the light beam, much as Einstein dreamed about riding a light beam at the age of 16. Not quite to the speed of light, but to a fifth of it, or 100 million miles an hour. Such a system could reach Mars in less than an hour, reach Pluto in days, pass Voyager in under a week, and reach Alpha Centauri in just over 20 years. Once there, the nanocraft could image any planets discovered in the system, test for magnetic fields and organic molecules, and send the data back to Earth in another laser beam. The engineering challenges are immense. The nanocraft must survive extreme acceleration, cold, vacuum, and protons, as well as collisions with junk, such as space dust. Then we would need to keep the nanocraft functioning for 20 years in the frozen void, so they can send back signals across 4 light years. Of course, this would not be human interstellar travel, even if it could be scaled up to a manned vessel. But it would be the moment when human culture goes interstellar, when we finally reach out into the galaxy. We are standing at the threshold of a new era. Human colonization on other planets is no longer science fiction. It can be science fact. The human race has existed as a separate species for about 2 million years. If humanity is to continue for another 1 million years, our future lies in boldly going where no one else has gone before. I hope for the best. I have to. We have no other option. Intelligence is central to what it means to be human. Everything that civilization has to offer is a product of human intelligence. DNA passes the blueprints of life between generations. At some point during our 13.8 billion years of cosmic history, something beautiful happened. Information processing got so intelligent that life forms became conscious. Our universe has now awoken, become aware of itself. I regard it a triumph that we, who are ourselves mere stardust, have come to such a detailed understanding of the universe in which we live. I think there is no significant difference between how the brain of an earthworm works and how a computer computes. I also believe that evolution implies there can be no qualitative difference between the brain of an earthworm and that of a human. It therefore follows that computers can, in principle, emulate human intelligence, or even better it. It's clearly possible for something to acquire higher intelligence than its ancestors. We evolved to be smarter than our ape-like ancestors, and Einstein was smarter than his parents. When an artificial intelligence, AI, becomes better than humans at AI design, so that it can recursively improve itself without human help, we may face an intelligence explosion that ultimately results in machines whose intelligence exceeds ours by more than ours exceeds that of snails. When that happens, we will need to ensure that the computers have goals aligned with ours. For the last 20 years or so, AI has been focused on the problems surrounding the construction of intelligent agents, systems that perceive and act in a particular environment. As a result of this recent work, there has been a large degree of integration and cross-fertilization among AI, machine learning statistics, control theory, neuroscience, and other fields. As development in these areas and others moves from laboratory research to economically valuable technologies, a virtuous cycle evolves, whereby even small improvements in performance are worth large sums of money, prompting further and greater investments in research. There is now a broad consensus that AI research is progressing steadily and that its impact on society is likely to increase. Success in creating AI would be the biggest event in human history. Unfortunately, it might also be the last unless we learn how to avoid the risks. Used as a toolkit, AI can augment our existing intelligence to open up advances in every area of science and society. However, I fear the consequences of creating something that can match or surpass humans. The concern is that AI would take off on its own and redesign itself at an ever-increasing rate. Humans, who are limited by slow biological evolution, couldn't compete and would be superseded. And in the future, AI could develop a will of its own, a will that is in conflict with ours. Others believe that humans can command the rate of technology for a decently long time, and that the potential of AI to solve many of the world's problems will be realized. Although I am well known as an optimist regarding the human race, I am not so sure. In the near term, world militaries are considering starting an arms race in autonomous weapons systems that can choose and eliminate their own targets. While the UN is debating a treaty banning such weapons, autonomous weapons proponents usually forget to ask the most important question. What is the likely endpoint of an arms race? And is that desirable for the human race? Do we really want cheap AI weapons to become the Kalashnikovs of tomorrow, sold to criminals and terrorists on the black market? Given concerns about our ability to maintain long-term control of ever more advanced AI systems, should we arm them and turn over our defense to them? The best time to stop the autonomous weapons arms race is now. In the medium term, AI may automate our jobs to bring both great prosperity and equality. Looking further ahead, there are no fundamental limits to what can be achieved. There is no physical law precluding particles from being organized in ways that perform even more advanced computations than the arrangements of particles in human brains. Machines with superhuman intelligence could repeatedly improve their design even further. One can imagine such technology outsmarting financial markets, out-inventing human researchers, out-manipulating human leaders, and, potentially, subduing us with weapons we cannot even understand. A superintelligent AI will be extremely good at accomplishing its goals, and if those goals aren't aligned with ours, we're in trouble. You're probably not an evil ant-hater who steps on ants out of malice, but if you're in charge of a hydroelectric green energy project, and there's an anthill in the region to be flooded, too bad for the ants. Let's not place humanity in the position of those ants. We should just plan ahead. Fortunately, technology pioneers Bill Gates, Steve Wozniak and Elon Musk have echoed my concerns, and a healthy culture of risk assessment and awareness of societal implications is beginning to take root in the AI community. In January 2015, I, along with Elon Musk and many AI experts, signed an open letter on artificial intelligence, calling for serious research into its impact on society. Elon Musk and I sit on the Scientific Advisory Board for the Future of Life Institute, an organization working to mitigate existential risks facing humanity, and which drafted the open letter. This called for concrete research on how we could prevent potential problems, while also reaping the potential benefits AI offers us. In October 2016, I also opened a new centre in Cambridge. The Leverhulme Centre for the Future of Intelligence is a multidisciplinary institute dedicated to researching the future of intelligence as crucial to the future of our civilization and our species. Recent developments in the advancement of AI include a call by the European Parliament for drafting a set of regulations to govern the creation of robots. Somewhat surprisingly, this includes a form of electronic personhood to ensure the rights and responsibilities for the most capable and advanced AI. A European Parliament spokesman has commented that as a growing number of areas in our daily lives are increasingly affected by robots, we need to ensure that robots are and will remain in the service of humans. A report presented to the Parliament declares that the world is on the cusp of a new industrial robot revolution. It examines whether or not providing legal rights for robots as electronic persons, on a par with the legal definition of corporate personhood, would be permissible. But it stresses that at all times researchers and designers should ensure all robotic design incorporates a kill switch. Lorna Brazell, a consultant at the multinational firm Osborne Clarke, says in the report that we don't give whales and gorillas personhood, so there is no need to jump at robotic personhood. The report acknowledges the possibility that within a few decades, AI could surpass human intellectual capacity and challenge the human-robot relationship. Opportunities for interacting with the world without having to be physically present are increasing rapidly. As you can imagine, I find that appealing. How many times have you wished you had a double who could share your workload? Our cities are already full of machines that extend our capabilities, but what if we could be in two places at once? We're used to automated voices on phone systems and public announcements. Now, inventor Daniel Kraft is investigating how we can replicate ourselves visually. The question is, how convincing can an avatar be? How we connect with the digital world is key to the progress we'll make in the future. In the smartest cities, the smartest homes will be equipped with devices that are so intuitive they'll be almost effortless to interact with. Recent AI landmarks, such as self-driving cars or a computer winning at the game of Go, are signs of what is to come. Enormous levels of investment are pouring into this technology. In the coming decades, it will permeate every aspect of our society, intelligently supporting and advising us in many areas, including healthcare, work, education, and science. We cannot predict what we might achieve when our own minds are amplified by AI. Perhaps with the tools of this new technological revolution, we can make human life better. For instance, researchers are developing AI that would help reverse paralysis in people with spinal cord injuries. Using silicon chip implants and wireless electronic interfaces between the brain and the body, the technology would allow people to control their body movements with their thoughts. I believe the future of communication is brain-computer interfaces. There are two ways: electrodes on the skull and implants. If we can connect a human brain to the internet, it will have all of Wikipedia at its resource. The world has been changing even faster as people, devices, and information are increasingly connected to each other. Computational power is growing, and quantum computing is quickly being realized. Quantum computers will change everything, even human biology. There is already one technique to edit DNA precisely, called CRISPR. The basis of this genome editing technology is a bacterial defense system. It can accurately target and edit stretches of genetic code. How far we can go with genetic engineering will become an increasingly urgent question. Human intelligence is the result of generations of natural selection, of those with the ability to adapt to changed circumstances. We must not fear change. We need to take learning beyond a theoretical discussion of how AI should be, and to make sure we plan for how it can be. We stand on the threshold of a brave new world. Our future is a race between the growing power of our technology and the wisdom with which we use it. Let's make sure that wisdom wins. A century ago, Albert Einstein revolutionized our understanding of space, time, energy, and matter. We are still finding awesome confirmations of his predictions. Where did Einstein's ingenious ideas come from? A blend of qualities, perhaps? Intuition, originality, brilliance. Einstein had the ability to look beyond the surface, to reveal the underlying structure. He had the courage to pursue ideas that seemed absurd to others, and this set him free to be ingenious, a genius of his time and every other. Many of Einstein's discoveries came from his ability to reimagine the universe through thought experiments. At the age of 16, when he visualized riding on a beam of light, he realized that from this vantage, light would appear as a frozen wave. That image ultimately led to the theory of special relativity. 100 years later, physicists know far more about the universe than Einstein did. Now we have greater tools for discovery, such as particle accelerators, supercomputers, space telescopes. Yet, imagination remains our most powerful attribute. With it, we can roam anywhere in space and time. My job is to try to figure out how the universe works using the laws of physics. If you know how something works, you can control it. It sounds so simple when I say it like that. I have been lucky to be alive through what has been a glorious time in my chosen field, cosmology, the study of the origins of the universe. The human mind is an incredible thing. It can conceive of the magnificence of the heavens and the intricacies of the basic components of matter. Yet for each mind to achieve its full potential, it needs a spark, the spark of inquiry and wonder. Often that spark comes from a teacher. When I was 14, my teacher at my school in St Albans, Dikran Tata, showed me how to harness my energy and encouraged me to think creatively about mathematics. He opened my eyes to maths as the blueprint of the universe itself. However, education and science and technology research are endangered now more than ever before. When I started out in the field in the 1960s, cosmology was an obscure branch of scientific study. Today, through theoretical work and experimental triumphs such as the Large Hadron Collider and the discovery of the Higgs boson, cosmology has opened the universe up to us. There are big questions still to answer, but we know more now than anyone could have imagined. But what lies ahead for those who are young now? Without speculating too wildly, there are trends we can see and emerging problems that we know must be dealt with. Among the problems are global warming, finding space and resources for the massive increase in the Earth's human population, rapid extinction of other species, the need to develop renewable energy sources, the degradation of the oceans, deforestation, and epidemic diseases, just to name a few. There are also the great inventions of the future, which will revolutionize the ways we live, work, eat, communicate, and travel. There is such enormous scope for innovation in every area of life. We could be mining rare metals on the moon, establishing a human outpost on Mars, and finding cures and treatments for conditions which currently offer no hope. I believe the future of learning and education is the Internet. In a way, the Internet connects us all together, like the neurons in a giant brain. And with such an IQ, what cannot we be capable of? I don't believe in boundaries, either for what we can do in our personal lives or for what life and intelligence can accomplish in our universe. We stand at a threshold of important discoveries in all areas of science. Without doubt, our world will change enormously in the next 50 years. We will find out what happened at the Big Bang. We will come to understand how life began on Earth. Through scientific endeavour and technological innovation, I am optimistic that we will ultimately create viable habitats for the human race on other planets. We will transcend the Earth and learn to exist in space. And one final point. We never really know where the next great scientific discovery will come from, nor who will make it. So remember to look up at the stars and not down at your feet. Try to wonder about what makes the universe exist. Be curious. Unleash your imagination. Shape the future.